Good day. Hopefully you have some PowerPoint notes that say the common ion effect. We're going to try to do this in one video, but if it seems to take too long, I'll split it up. Common ion means exactly that. You'll have an equilibrium of a salt that's not totally soluble dissolving, and we'll have the presence of one of those ions already available in solution that's going to reduce the overall solubility. So that's why it says when a salt's dissolved in a solution that already contains one of its ions, its solubility decreases. This is the common ion effect, and it's related to Le Chatelier's principle. So if we look at this equilibrium, if we had a solution of calcium nitrate or sodium carbonate that we're trying to dissolve this in, means we already have these ions. That's going to be higher. It shifts it left, shifts the equilibrium left, so less of this can dissolve. Alrighty. So I think we have 3 examples here. We'll see how far we can get. So we're given a KSP. If we weren't, we just look this up on our table of solubilities. And we're told that we have this solution, a 0.010 m. And we say, whoa, I see Cl there and Cl there. So that's going to be our common ion. We know sodium chloride is totally soluble, so we already have this concentration of chloride present. So if we did this as an ice chart, what we find is we're not just starting with pure silver chloride and seeing how it dissolves. What we have is we already have the chloride present. So a certain amount of this is going to dissolve, and that's going to increase the silver concentration. We're going to add that amount to this 0.010, but this X value is going to be so small, it won't be significant, and so it took hours to find the approximately equal symbol. So in fact, we're already going to have this concentration, boom, 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 present of chloride. So now it's time to get our KSP expression. And what we know from the previous slide is that the silver was X. We don't know what that is yet. We know the chloride was 0.010 m, and we know the KSP. So to isolate the X, we're going to take this number here, divide it by 0.01, and hopefully you do not need a calculator for that. So we end up with 1.7 times 10 to the minus 8, big M. And that value of X is our solubility. Now just at the bottom, if we dissolve silver chloride in water, pure water, its solubility would be close to a factor of 1,000 times greater, because we wouldn't have this chloride ion concentration shifting the equilibrium to the left. Well, I think we're rolling okay. Question 2 and 3 are going to be largely the same kind of game. So we have, in this case, our common ion is going to be the hydroxide, because we see it here, and we see it here. And we can see the hydroxide concentration that's present already as the 0.10 m, and we're given a KSP. So same kind of deal, the magnesium becomes X, 0.10. The 2X is going to be so small because we have a small KSP, and so it's going to be 0.10 m, as we were told there. So we're just as before, write out our KSP expression and solve for the unknown. So we know the Mg2 plus was X, we know the OH minus was 0.10, and we got to square it, so that's going to be 0.01. Which is 1 times 10 to the minus 2. And we're going to take that and divide by it, and we end up with 1.2 times 10 to the minus 9 m. So that's what happens when we dissolve in a solution that already contains hydroxide ions. If we compare it to what it would have been in pure water, it would have been significantly more soluble. And those are calculations you can do and double check if I've done it right. Now we have another common ion effect example. In this case we see we have lead here and lead here. So we've attached nitrate totally soluble. So that's going to be our concentration of lead ions that we already have. We'll do our ice chart. And so we have 0.10, that's the lead there already, adding the X, very small amount, and so no significant change, so that's our concentration of lead ions. But this time we have a 2X, because we have a 2. Every time this dissolves, it makes twice as much iodide. So that's the real trick in this question. Now we're going to take this 2X and this 0.10, and we're going to plug them into the KSP expression. So what do we get? You say, how did I get that? Well, I went 2 squared is 4, and 4 times 0.1 is 0.4. X squared is x squared. So I'm taking 1.4 times 10 to the minus 8, and I'm dividing by 0.4. So I actually will get a number that's bigger than 1.4 times 10 to the minus 8. And I also have to then square root it. So I have to divide by 0.4, take the square root, and I end up with 1.9 times 10 to the minus 4, big M. And again, if I did this in pure water, it would be slightly more soluble in pure water than this situation. So hopefully those questions are making sense and how you attack them. Be organized, know what KSP expressions tell you, and know how to use the ice chart.